Okay, the point of this video is to prove a result that we used in class, which is that the center of mass moves, of a system moves like a point particle, with all of the mass of the whole system under the net external force acting on the system. So, in other words, that if we consider the acceleration of the center of mass times the total mass of the system, mass of system, sum of all the masses in the system, that motion will be as though the external forces acting on the system were exerted on a point mass with the mass of the whole system. Okay, that's what we're going to prove. So how can we do that? We're going to start with the definition of the center of mass, which is that the position of the center of mass is a weighted average of all of the little masses with their positions. And then we're going to take the derivative of this. So take the derivative of both sides of this equation. So that's dr dt of the center of mass, which is v center of mass. And then we want to take the derivative of the right side of the equation. And so all our mass terms are just constant, so we can move our derivative all the way in here and take the derivative with respect to each of these positions. So the derivative of a position of a particular mass is the velocity of that particular mass. So we've got 1 over the total mass times the sum of all the masses, or each mass times each velocity. Right, and now we're going to do that again. So we're going to take another time derivative of both sides of this equation. So when we take the time derivative of the velocity of the center of mass, that will give us the acceleration of the center of mass. And then again, our mass terms are constant. So we're going to pull our derivative in and take the derivative of each velocity. So we've got the acceleration of each object. Okay. Now we're going to multiply, or to multiply everything by the total mass. Okay, so on the left here we've got MACM, and then on the right we've got MIAI. Okay, now we can use Newton's second law to say that this term that I just highlighted is equal to the force on each object. Okay? And then now we can think of each point inside the object as having a set of forces that are internal to the system as a whole and external to the system as a whole. Okay, so each object has F now I is F internal I plus F external I, where these internal forces are forces on other objects in the system, and this external F is forces from outside the system. Okay, so we're going to write our last equation as the sum of all these internal forces plus the sum of all of these external forces. Now, using Newton's third law, we know that this term must sum to 0, okay? Because for each of those internal forces, there is an equal and opposite force. So if it's a force from another object inside the system, then that second object exerts an equal and opposite force. So when we add up all those internal forces, they all sum to 0. And so we can drop that term, and we have what we were trying to prove, which is that the motion of center of mass, that acceleration of the center of mass times that total mass of the whole system, is equal to the sum of the external forces on the object. Okay? In other words, the center of mass moves as though it's a point particle with mass m under that's operated on by the net external force on the system.